Okay, perfect. So today we are going to discuss how to design a system for Uber. Now, before I start discussing this, a couple of things which I want to point out today. First of all, I didn't get so much time to actually create a good PPT for this particular system design. And also, just because I did it in hurry, so most of the things I will be telling you guys from my memory or from my uh, as when we reach that point, I'll keep telling you guys, and if I miss anything, then probably it will be best if you guys point that thing to me and I can catch up on that. And second thing is, since Uber is not so simple design, so this discussion can be a little longer, but I will try to keep as short as possible so that we can finish it within at least 1 hour, just like all other sessions. And later on, I might do another session, part two for the Uber, where I will keep it a little longer and we'll discuss in more detail. But this session should be enough to get you started to study for the Uber system design interview anyway. So by that, I will start the session. Um, just like all the time, I have more or less similar content. We'll think about the requirements first, then we'll think about how much capacity do we need based on some assumptions. Then we will see what are the key concepts which we are going to use in our database, in our design. And then we'll see how the database looks like. And then we will go to the actual design, and then we will see what we could have done better. Okay, let's go to the requirements first. So the Uber, most of you will be all anyway familiar with the Uber, so it's no brainer in coming up with the functional requirements. But when you are in actual interview setting, then it's imperative that you ask your interview and discuss on the requirements and make sure that you have clearly defined your requirement scope, that you know that which features are not part of your design and which features are part of your design. It's very important to have that understanding with the interviewer first before even starting anything with the design. So that's when the requirement phase comes first. And during the requirement phase, actually it shows that a lot of maturity in you. If you ask uh, so many requirement uh, questions upfront to the interviewer, then the interviewer will get to know that you do not think about the problem superficially. At least you go a couple of levels deep and think thoroughly about the problem and then start designing the system. Whereas the people who do not have so much experience in designing complex systems, they'll jump into the solution right away without thinking much about what exactly they wanted to make. So that's the true differentiator, and take advantage of that. And the functional requirements are basically: passenger can see the nearby cabs based on its location, obviously. Passenger can request the cab. Driver can accept the cab request. Driver can notify the availability. For example, driver can say, okay, from now on, I'm not available for cabs. And what are the non-functional requirements? Of course, it should be highly available and it should be consistent. For example, if a driver is in at a particular location, then you cannot afford to lose that consistency. You cannot show that driver has reached at some other point, and if there is even some small amount of delay, then it will create a problem. To the passenger, it will show that driver is somewhere at location A, whereas because of your inconsistent design, actually driver will be at some other position, and which will create a bad user experience and very bad mismanagement on your part. So these are the more or less requirements, and some assumptions. We'll assume our application is huge. Let's say 300 million customers, well, in 1 million cab drivers. Not all of the customers as well as cab drivers will be active all the time. So we can safely say that around half of the cab drivers will be active at a time, and around 1 million daily rides will happen. I left out the capacity estimation, where we estimate about how much storage capacity do we need, how much network bandwidth do we need. I've left out those calculations. As I told, I didn't get much time to prepare this PPT. So I left out so much detail, and I will just go straight away to the design and start discussing things. And as always, in case of any questions, reach out to me now, or you can reach out to me later in my Slack channel. And I will upload this video, and I will probably upload this PPT after some more enhancements later on. Okay, so some key concepts which we need to understand before jumping into our design, which we are going to use in our system design, is first is geohashing, and second is chord tree. So geohashing is a generalized concept where we divide the whole earth into so many number of grids that some area, just like you can see in the diagram, we have divided the whole earth into small square shaped grid, and each grid contains some chunk of area. So if you zoom on some grid, then you can have further subdivision of that grid into further subgrids, and then so on. So when you zoom out your map and zoom in your map, that this is what happens. So when you zoom out your map and when you see the whole earth as a whole, then this is what you see. But when you zero on some portion, then you zoom out on that particular portion, and then you see the grids in such a way. So this is the whole concept of maps. This is how the maps have been designed. And as you guys know that Uber is heavily based on maps. So this is what it is going to depend on. This is the major core functionality which shows you the location and every other data on the Uber UI. Now the second thing is chord tree. So geo hashing is good, fine, but how do we store the data? How do we store the grids and all the relevant data in our computer world, in our system world? We need to have good mechanism where we can translate that division of grids and all the related data and somehow save into our system, so that first it is easy to search the locations, and then it is easy to manage the storage. So that's when the chord tree comes out. So the chord tree saves in such a way that this grid information is saved in such a way that this is how it is represented. Chord tree, by the name, as you can figure out, that each node will have 4 children, and these 4 children in turn they have their own 4 children, and so on until it reaches the leaf. So just like binary tree it is chord tree. So why chord tree? As you can see that each grid, this is the black square is one grid. Each grid is divided into 4 regions, and when you zero in on one of the 4 regions, then that region itself will be divided into 4 more regions, and so on. So as you can see, there is a consistent hierarchy of the data. First we have a huge grid of whole world, and then we have chunks of grids where we have small regions, and then these chunk of grids are further divided into 4 grids. So if we imagine start from our top level grid, which is whole world, then we can uh, very comfortably divide that whole world into 4 individual grids, and then we can zero in on one of those grids, and in turn we can divide that whole zeroed in sub-region into further 4 pieces, and so on. Am I making any sense? Is there any doubt? Okay, I hope not. So the data, this particular data we are going to represent in chord tree, and both these concepts we are going to use in designing our Uber database. So the problem in Uber is it's very much available as well as consistent. So as you can see that if the system is always consistent and always available, it is extra hard problem to solve, because managing both the things at highest level is very difficult problem. If we could compromise on consistency for a little bit also, it will help us ease into design. Why? Because we can pre-calculate the result, and we can show the old data into the UI because consistency was not important. But in this case, we can't afford to do that. We always want to see the real-time data. And let's go with the database first, how we are going to store the database. So I'll discuss a couple of things in the database here. First, we'll go over the generalized how many tables we can have, how we can structure our data in the RDBMS format. And then we will see that what all problems it can have. And then we will discuss probable solutions to the database problems. And then we will move on to the actual design. As you can see that we have individually 3 tables. One is passenger table, no brainer, driver table, no brainer. And then we have cab table. Now the cab table is important. Cab table stores the longitude and latitude information for that particular cab. And actually, the passenger will also store the longitude and latitude information in its cab, but uh, that data is not so that data needs to be updated every now and then, because you can move as well as cab can move, and every time when you move, your position changes and your LA and latitude and longitude basically changes, and you have to update it. So this is very simplistic design. You are not going to design in the real world, but you can start with this design. Now let's think of the trade-offs. As you can see, first trade-off we already discussed, that this is not scalable, that if RDBMS gets updated all the time, then it is not a good design. So what we need to do, we can move out this longitude and latitude information in a key value pair, which is more right right heavy and right we can comfortably write to that. So we can use something like DynamoDB or any key value pair data structure where we have cab ID mapped with the longitude latitude information. So that way we can solve that problem, at least for now. And whenever we need to know the current position of the cab, we refer to that key value pair index and we will figure out, okay, what is the current state of this cab. All right, so we solved at least one level of problem. Now, what is this grid ID 1 and grid ID 2? So I want to diverge a little bit here and give you a little sneak peek into how we are going to actually name our grids. As you can see, first the whole world was divided into 4 grids: 0, 1, 2, 3, right? Then we zeroed onto the 2 grid. We went this. Now 2 grid is further divided into 4 grids. Now we appended 0, 1, 2, 3 to the existing 2 value. So the first character, which is 2, represents the bigger grid. And the second character, which is 0, 1, 2, 3, represents the second order of the grid, which is second level of the grid. Understood?
Yes.
And similarly, if we go further down, then we can see this 13 grid is further divided into 4 grids. So 13 is again appended with 0, 1, 2, or 3 as per uh, which particular grid you are referring to out of all the 4 grids for region 13. So this we can keep doing this forever, right? As you can see, if you go further one down level, you can if you zero in on this 130 grid, then you will have further grids like 1301, 1300, 1302, 1303, right? And you can keep on doing that. And that's what we are going to store here. So grid 1 information is first level of information. Grid ID 2 is second level of information. So grid ID 1 can be 0. Grid ID 2 can be 0, 1. Grid ID 3 can be 0, 1, 1. Right? As we go further deep into the space, we will keep on incrementing one new character to the grid number, and we will keep storing that. Now, why I wrote dot 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 dot? To reach a particular cab, you certainly have to do multiple hops into your chord tree structure, and based on that you can have a separate column for that. Now you will ask why I need to have a separate column. Because I need to index these grids all the time. I need to index the grid at the continent level. I need to index grid at the country level. I need to index grid at even a district level, or even city level, right? So this each column can be indexed separately. And when you want to search a particular person, then you can pick a particular column and run the search that person, that cab, in that index, and that's how your search will be easier. Although there is redundancy of data, that we are technically, you can argue that we are technically storing the same data in multiple grids at different level of details, but that's fine. We can go, we can compromise some kind of redundancy when it comes to availability. So if we organize our data that way, we will be able to search more quickly. Although even if we utilize some amount of more memory, that should be fine. That trade-off is perfectly fine with us. All right. So this storage mechanism will be good for our DBMS data schema. Any doubt in current schema?
I just had a quick question.
Mm-hmm.
Like, are we going to use like a combination of a MySQL and a NoSQL database? Like,
Yes.
okay, so like how will be managing both those things? Like, we are just making changes to the NoSQL database for that longitude and latitude thing,
Mm-hmm.
and it will be scalable. And the MySQL won't be scalable because like a relational database is not very much scalable. So
Correct. So as I showed you, right, first you can start your naive design with storing longitude, latitude in the RDBMS itself. You can further optimize it by separating longitude, latitude information into a NoSQL database like key value pair, right? So that
yes,
was the first optimization we did. Further, similarly, as we will embark on new and new use cases where we need more and more read heavy data, and we don't want generally to your indexing cost becomes more and more. At first, of course, first optimization in RDBMS you do is start indexing more and you start sharding the data. But at some point, these solutions will basically run out of fuel. You will definitely need to have some ready-made, ready storage, just like key value pair. So that's what you're gonna do. And one example I just told, that longitude, latitude one, you can separate out and keep it out. So that's how you will combine the RDBMS data as well as the NoSQL database, and you use your Uber system to function properly. Whereas you can also actually opt completely out of RDBMS. You can say that I don't want to deal with RDBMS at all because there's so much of a hassle. You can completely go to NoSQL database, which will be, I think, which will be useful. There's a very good case that you don't need RDBMS database in this case, because NoSQL database will be more or less flat structure, as I previously talked to you guys, like it is more beneficial. So writing consistently and reading consistently can be managed in better way rather than all the overhead which comes along with the RDBMS. Although RDBMS will come with a lot of consistency, and NoSQL database might face difficulty in that area, but when it comes to compromising on high reading and writing speed, I think you can completely give away this RDBMS database and completely map it to NoSQL database like MongoDB, Cassandra, or whatnot, or combination of NoSQL databases.
okay, makes sense. Thank you.
Yeah. So, but currently I wanted to describe that how when you zoom in or zoom out in your map, how does that functionality work? I wanted to show you that you technically have multiple, you can imagine multiple columns in some database table somewhere, and as in when you move in, so dynamically one column gets picked up, and you pick up that column and you start searching locations in that column. So that's how you zoom in and zoom out functionality works. I wanted to describe that concept, and I think you guys understood. If there is any doubt, then please ask me. Okay, I'll move on further then. I have not done a good design in this one, honestly, but this is what the bare basic design which I could come up in quick time. I will discuss more what we can do more further along while I talk, but you can see that this is the bare backbone of the whole design system. As you guys can see that you have two flows. One is driver flow and one is cab flow. Uber has its own standalone driver app, and you have your own Uber consumer app where you can book the cabs and driver can accept the cab from the driver cab. And both of these flows are written here. Both the uh, flows will go to some kind of load balancer. You can make an argument here that probably one load balancer will not be enough. You can have multiple, and probably few load balancers are only dedicated to the driver one, few load balancers are only dedicated to the cab one. You can have all those arguments, but abstracting out everything else, technically both of these cab and driver will go through a load balancer. What's the purpose of the load balancer? Load balancer will redirect that to WebSocket server. Now, I have already briefly discussed what web server is, WebSocket is. So, but I will rephrase again what exactly WebSocket does. So every server has limited number of connection, like by design. Your laptop has limited number of simultaneous connections at a time, and so does any server will have. But you have millions of cabs and millions of drivers, and you can't afford to have a established connection for each of those cab and drivers at the same time. You don't have technically that much space, and if you want to achieve that, probably it will become very costly affair. So what is done, right? This WebSocket API is an abstraction on top of underlying sockets, and this WebSocket is asynchronous, and socket is basically synchronous. Once you make a connection with a socket, that remains forever, not forever, that remains for some time, and that socket is basically blocked. You can't use that socket for anyone else. That socket is basically dedicated to that particular connection. But in WebSocket case, it abstracts out. You can have simultaneously 1 million connection to WebSockets. And under the hood, these WebSockets will basically be using the same number of sockets which you were using previously. But since these are working asynchronously, basically one socket is not attached to one particular connection all the time. That's when they can switch between different sockets, and under the hood, they can utilize same number of sockets to give you an impression that you are connected to 1 million people all the time. So that's the abstraction it has been done, and it's many applications use WebSocket in these days. I think I discussed more about WebSockets in FB Messenger some design interview. I'll encourage you guys to go ahead and watch that WebSocket video, at least that portion of the video, to understand more about WebSocket. So why we used WebSocket server here? Because we have that need. We need a user to be constantly connected to my server, right? When you are in the cab, then you can see that you are constantly connected. You can see the route of your cab, that from where it is going to where it is going, which path it is taking. So all that while you are 100% connected to the server, and you need one dedicated connection. Similarly, driver is also dedicatedly connected to the WebSocket server at the same time. So as you can see, you have a need of a sustained connection over a period of time, and you don't need one, you don't need two, you need millions of that. And WebSocket is a good candidate here. We use WebSocket. But since WebSocket functionality is too heavy, that's why we dedicated a complete server to manage its functionality on your own. Right? To maintain those WebSocket servers, a dedicated web server is needed. It will have much more than just maintaining the WebSocket connection. That's why it's a complete server. Functionality won't be limited to just maintaining WebSocket server connection, but it will be much more than that. All right. So till now we started from cab or driver and we reached to the WebSocket server. Now we will go to individual servers. Let's say WebSocket detects that this particular request is coming for cab, request cab. Then it will go to passenger server and it will try to fetch the cabs from the system. If it is driver who is sending the update location, basically update location, I mean the driver won't be still all the time, right? Driver app will constantly send out update location to the backend, so that the driver's location is constantly the correct consistent one in the system. So that request will be coming here, and this server's uh, task will be to update the constant correct location into the system. Okay, both of these flows are like till now good.
Yes.
Okay, so this both the flows which eventually end here, these region services. We'll discuss more about these region services in our next call, because this call is about to get. Okay, we can continue our conversation here. Are you guys able to hear me?
Yes.
Okay, perfect. So where were we? So we reached our system design to flow here. Both the flows basically ended up here. The cab flow ended up in passenger server. Driver flow ended up in cab server. So driver wants to constantly update the information and all other things which driver app wants to do. It will end up here. Cab basically ends up here, fetching the cab, seeing the connection, uh, observing the current cab. All the things go here. Now what is this? Uh, as you can see that the Uber is basically working all over the world, right? And we want to divide our requests based on the geography. For example, your city might have its own dedicated server, or let's say your zone, the grids per grid, we can have many servers based on as many number of grids we can have, depending upon how many grids a particular server can handle. We can divide a server based on that. That's why I have written region 1, region 2, and so on. So these servers will be there based on the number of regions you have divided your servers in to serve the traffic. Now, what happens if one of the server basically fails here? So that's when the concept of system design comes, this consistent hashing comes. So what happens in consistent hashing? Um, Suppose this is region 1 server and it is handling grid 1 to 10, and then region 2 is supposed to handle grid number 11 to 20, just for example, and this region 3 is handling grid 30 to 40. Now what if this particular region 2 fails? Then what happens in consistent hashing, that this uh, uh, first of all, in consistent hashing, any request can go to any server. So if my request for grid 1 reaches region 3, then region 3 basically knows that which particular guy stores the which particular guy is responsible for handling the request for region 1. Then this guy will somehow redirect the request to this region 1 server. And once it reaches region 1, then this guy knows how to process the request and it will go on processing the request. Similarly, let's say when region 2 goes down, then somehow these servers basically get to know that this region 2 has gone down, and the region 2 was responsible for serving 20 to 30 uh, grids, but since region 2 is not there, someone has to process. So this burden automatically passes on to region 3. So now region 3 handles from 20 to 40 for 20 grids at the same time. No doubt that there will be some uptick in traffic for region 3, but for now it will be okay. So that's how the consistent hashing grid works. First concept is all the regions know that which server is supposed to process what. That is point number one. Second point is, if one of the regions fail, then in the circle, whoever is the next guy in the clockwise circle or anti-clockwise circle, all the requests basically pass on to the next server, and this goes on. And similarly, if suppose you want to insert a new server, your three server setup is not working anymore, you want to insert one more server in between, definitely you can insert in between. Now what was happening here? This guy was this guy was managing 10 to 20, this was managing 20 to 30, this was 30 to 40. Now if you insert in between, then this guy starts managing 30 to 35 and this guy takes 35 to 40. So if you see that order, that remains same: 20 20, 20 to 30, 30 to 35, and 45 30, 35 to 40 here. So as you can see, that order remains. So consistent hashing gives you flexibility around failures, gives you flexibility around scaling. There's much more to consistent hashing. I think I briefly touched upon here, but you should definitely, guys, read up on consistent hashing. It is one of the most asked point, where your system design interview is definitely going to drill you down and see whether you really understand consistent hashing or not. So now imagine this box will basically serve some request. Any one of of the region servers will going to serve that request. Once that region serves the request, now the request will fall back on the database. But we smartly put one cache here just in front of the database, and the function of cache will be to give you the most frequently searched data out there. For example, if there is an event going on in some stadium, and you definitely will have a request for caps for that particular region, like at the same time, you can cache some of the data here instead of directly fetching everything from the database. So you can utilize cache here. I'm not sure as of now that what exactly data you can put in the cache, but conceptually, if the data is very frequently accessed, then instead of going to the database, you can pre-save that data in cache and serve that request from there instead. And this cache can have many mechanisms. That expiry of the data can have mechanisms like whichever data is not recently used, it can be removed from the cache, and a new data can enter which is more frequently used. So that way we can always have fresh data which is more frequently used, and we keep discarding old data which is less frequently used now, but the data was which was frequently accessed at some point of time in the past. So that way we can manage data access. So this kind of mechanism is called recently used kind of mechanism in cache, also called LRU cache. And yeah, LRU cache is one of the elementary system design questions too, by the way. So just look up on that. How do you design LRU cache? So this was the overall flow for our system. How a driver is going to interact with the system, how a cab is going to describe, how you as a passenger is going to interact with the system, and how system is going to respond in different situations. This was the very, very high level basic of the system design. Now comes the part where we want to partition the data. Let's say you have database just like you have seen here. Yeah, this database. Definitely one database server won't be enough. Somehow you have to divide the database into multiple horizontal databases where you can serve the request based on the request type. So first, of course, approach is region-based approach. For one particular region, you store data in one database, another region you store in another database, and so on. Right? But this has one downside. Downside is that some of the regions will contain that populous cities like New York, and that database will be super heavy. Whereas another database which contains the region like Pacific Sea, that won't have anything. So there will be very imbalanced approach to your partitioning scheme, and you have to do something about it. That's the problem you started with, right? Because there was so much load on one server. That's why you wanted to divide the whole data into multiple servers. But you ended up facing the same problem here also, because one database server was more accessed and it had more data. So it basically made your database server super heavy. So what do? You basically store it based on the location's hash, location ID's hash. So all the cabs of New York will not be stored in one database server. So all these cabs will have their cab ID, and from that cab ID, you can calculate the hash. And based on that hash, you can divide the data for that cab into the database. Understood? Any problem in understanding the hash and how we are going to divide first the cab ID into the hash and then hash into the database? How we are going to divide the database based on hash? Any further explanation needed? Guys, speak out, please.
No.
Okay, perfect. So you understood how hash location based hashing is one of the better mechanisms to partition your data, right?
Yeah.
Now, I think I covered most of the stuff, but here one thing which I missed to explain more, I want to actually go deeper into that. Once you drill down to a particular region, to particular grid, you find some cabs are there. But let's say you reached a leaf of location, let's say my locality, you eventually drill down to my location, you eventually drill down to the very leaf node of the grid, which is at my place. And when I'm trying to request a cab, then you are trying to see in that grid that how many cabs are available. Unfortunately, let's say no cab is available in my grid. What happens in that case? You can't say as an Uber, you can't say that we don't have any cabs anymore. You want to push little more, right? So what do you do in that case? You basically look for cabs in adjacent grids, which is basically not definitely my grid, but you will go ahead and see in different grids which are adjacent to mine, and see whether if cab is available in those grids instead. How you are going to find out the adjacent grids? As you can see that these four grids are adjacent to each other. So one natural step is to just find out which of the four siblings this guy had. So these four siblings are basically very adjacent to each other, right? So if there is a way that if you found a leaf node and if you can find the siblings for that leaf node, these will be definitely the adjacent grids and you can make a search on that. Now the problem is basically boiled down to simple concept of finding the leaf node of a tree. So once I reach this particular guy, then I just need to find out which all three guys are adjacent to it. One way is go to the parent node and find out all the three adjacent grids. Another way is, and more basically I think a more used approach is, these all the four children are connected to each other via doubly linked queue. And once you reach any one of the leaf node, you can seamlessly navigate to other grids without any effort. But even if that approach doesn't work, then you want to go one more level up and see, do the search on that. So let's say all these four grids don't have cap, then you go to parent one and you find the siblings of that parent, and now you have bigger search area. And definitely you will find a cap, and you can keep on doing that till infinity, but generally that is not advisable. You can't do it infinity. Your system will run out of capacity, processing capacity. So you want to stop the search at some level that say, okay, cab is not available at all. Even after hopping multiple levels up the tree, I found out that in your area there is absolutely no cab. So that's when you see that cab not available on the Uber app. All right. So this was the missing part. What else I can discuss? Yeah, one more thing I can discuss actually. Um, Actually, two more things I can discuss. how you are going to fetch in pretty efficient way that which grid has how many cabs and which particular cabs. So as you can see, you can optimize that thing too in this your database. You can have a constant key value pair where the mapping, the key is the grid ID and the value will be the list of all the cabs available in that grid. So whenever you find you reach a leaf node of that quad tree and you want to access all the cabs surrounding in that region, in that grid, particular grid, all you have to do is just query that your key value pair database where you already have a mapping which is constantly being updated all the time, but you have ready-made mapping and you can immediately fetch away, okay, for the key, for the key, basically grid one, for the grid one, give me all the cabs which are already in the grid, and it will quickly give you the number of cabs and their relevant data directly without even querying your RDBMS and going joining multiple tables and seeing which belongs to which grid. So that will be pretty complicated solution. So that's where you can optimize that thing. But that that key value pair will also basically start growing at some point. But then what do you do when your data starts growing in your database? Obviously data sharding, right? You start sharding that to on some good sharding mechanism. Can be based on the hash of the grid ID or it can be based on the region ID. Depending upon how your data is being used and how much load your servers can sustain, you can pick one of the sharding mechanism and do away with. Okay, so that was one point I wanted to discuss. What else? Where else we can optimize actually data? Yeah, this is where. So if you imagine that if you want to organize whole world into one quad tree structure, as you can already see that it will be a huge tree, right? This is the top grid and then you bifurcate four and then four and four. By the time you reach to actual manageable grid where you can say, okay, I want to search the number of cabs in that particular grid, that will be like multiple levels deep in your tree, and that quad tree can become huge. So it's you need a mechanism to partition this quad tree also, in fact. So one of the mechanism is basically to bifurcate this quad tree into multiple pieces and store separately. And after a point, if you want to reach an quad tree for that particular region, you have to query another server instead rather than an in-memory quad tree here itself. Understood? So in summary, what I'm trying to say is one way is basically you can load whole quad tree in memory. That should be fine. And in memory, you can basically traverse this whole tree wherever you want and whenever you want. That is definitely not the problem. But the argument I'm trying to make is that the size of the tree might be bigger so that it won't be in, your server won't be enough to load whole of your quad tree in memory at the same time. In that case, you want to bifurcate the quad tree itself into multiple quads, smaller quad trees distributed into multiple servers. And as in when you are like going deeper into the quad tree, you jump into one server to another server and to another server based on the regions. So that way you can manage your quad tree. Any doubts and confusion still now?
No, Nish.
Oh, perfect. You guys are all intelligent. Okay, so I think this was it from my side. Um, but the last slide is what we missed out. We technically missed on almost everything. We designed the core feature of the Uber, whereas these are all extra functionalities which we never discussed and we never cared about, but they can be added in our system design, which will make our system design more complicated, but these can be added. First of all, estimated time. The moment you find that, okay, you want that cab and you book that cab, How do you know that how much time it is going to take? Easy solution is use your maps API. Your map already calculates the estimated time from one point to another point, Google Map, and you can use Google Maps API. Rather than calculating yourself, you can send the two locations to Google Map and ask that what is the estimated time for between those two locations, and you can display on your Uber dashboard, Uber UI. Another way is probably that data might not be so much good or enough for you. You want more customization on top of that. Still, you can query that ETA and use that ETA and combine more parameters to it and use and calculate your own custom ETA and display that instead. So that is the approach. Constant tracking of the cab, that as I already told, actually if you have constant connection with the server, then you can implement a functionality where there is always a signal every 4 seconds or 2 seconds between your server and your current location, so that your current constant location is basically updated on the map on the real time, right? So that kind of functionality you can develop. Call to cab without number, like we never thought about that. If you want to you call from your mobile to the cab, then how you are going to do it? Suppose including with number will be difficult to implement, but without number basically implements one more level above and makes it a little more complicated. And then what happens, the payment structure? Then payment structure comes along with its own complexity, that how much time cab is spent while waiting, how much time cab spent on the run, on the road, and how many passengers it was trying to carry. In case of shared cab, how much split it needs to do for which passenger. So all these things basically become more complicated when it comes to payment. Your interviewer might unfortunately drill down in one of these areas, and you have to keep on building from that. But I didn't discuss it, but I'm sure you guys can carry on from there. Another thing is price surge. Price surge is another very complicated topic. Price surge generally happens via some constant machine learning logic, machine learning real-time logic. So that particular model, which basically works on the number of incoming sessions and incoming connection requests to the WebSocket server, and based on some other parameters, it can decide, okay, there are so many connections coming from this particular area, probably there is a huge demand, but so let's increase the cap price. That's when your price basically surges up. But it, on the opposite side, if for one particular area, if there is no need for cap, no one is calling cap, then the price goes down. So that dynamic price calculation happens via machine learning model, and you feed real-time data into that machine learning model, and machine learning model basically it spits out a particular price for that moment. Correct. One more feature which I have not written down here is how do you implement shared cab. So if you book a share cab, then the cab is basically managing the trip for multiple people at the same time. But we discussed one happy case where you were the only customer and there were so many cabs, and that's when it happened. But think about the scenario when there are multiple passengers requesting the cab and multiple passengers are mapped to one cab. So how does that happen? There will be many different enhancements and tweaks in your current system design to cater that, but I will leave to you guys that you are going to study further and drill down more deeper into it and understand all these lying system design enhancements which can be done here. Another thing which I missed out on is how you are going to handle analytics part of it. All the systems, even Uber or any other system, basically is interested in analytics. Analytics meaning what is currently happening in the system right now, and they want to show in the dashboards. They want to analyze on top of that. They want to analyze to get insights that who is currently using my system, who is currently not using my system, what new feature needs to be developed based on past usage. So all those things happen here. So once the WebSocket basically server gets the flow request, the current discussed flow was that it will pass on to this server and this server. There is third more server where it will pass that information for further consumption of analytics. So generally that happens in some kind of messaging or streaming framework, because this is incoming data at a huge speed, right? You can say this is streaming data coming to you all the time. You can put up a message queue server here which holds that data for some time, and on the one end the data is ingested, on the other end there are systems which are eating that data and processing it for doing whatever you want. Either you can do either um, analytics, or you can do fraud detection, or whatever you want to do with that data you can do it, but that particular flow is completely separate from this data. So this is where that component will start coming. Another quick multiple things which I think you guys already know, but it will be helpful to reiterate more. What happens to the redundancy? We can't have one data, right? We should have duplicate data at multiple places, so that whenever this system goes down, we can redirect our traffic from this to the backup data. And that can be managed via master slave design, already discussed so many times. So that way you can achieve redundancy at this place. But and to achieve redundancy at the server space, we have already discussed that you can, on the go, you can insert more servers and remove more servers based on the capacity requirements. So that is one thing. Okay, covered a lot of things today. Yeah, go ahead. Someone was asking something.
So I also wanted to ask, like, you just discuss this further scope, like this all the extra features. Do you know where can we like get some more material about this further scope? Because it is really difficult to come out for the solution for this stuff. Like this is really complicated thing, I think.
Correct.
We can't
You
come.
are right. So there are some of my go-to resources are, first of all, obviously the engineering blog of any particular company which I am doing system design preparation for. That is my first go-to resource. The second go-to resource is high scalability site. There is a site called scalability.com, and there are so
Okay.
many articles written in that. So many people have described that how they would design, and how, some of the real people actually have written articles that how they have designed one particular component. So that site will be very, very helpful. And
Okay.
third is like random YouTube videos or some ad hoc blog written by someone. And but you have to do a lot of hard work actually to find the correct content to study one particular system design. There is no one place where they have written down all the things, and obviously it would have been like much easier, but unfortunately that's not the case.
Okay. Okay. Got it. And also over here in future scope, we can add like one more feature where the Uber is providing offers to different people. Like on the bills of their usage, they provide good amount of like they offer 50% off or 10% off or something like that. So that can also be added in the future scope, right? Like
Yeah,
that can be added as one of the feature as well.
yeah, definitely that can be added. Yep. You can actually append Uber Eats to here. Uber Eats technically uses the same infrastructure of the Uber, right? So your
Yes.
interviewer might say that, okay, I want to serve food also now. Now tell me how does that work? You have to add that also. That can be also the feature of it.
Yes. Yes. Right.
Okay, I think that should be it. In case if you have any questions, message me. I will be happy to answer you guys.
Sure. Thank you,
I
Avnish.
hope it was useful.
Yeah, it was really useful. Thank you.
Yeah,
Yeah. Thank you, Anish.
Thank
yeah,
you.
no problem. I'm sorry I didn't get so much time to prepare a detailed PPT this time. Next time I will make up.